I would like to introduce Maryam. Well, it's our great honor that Maryam is with us in the summer school. Thank you, Maryam, for coming. So Maryam got her bachelor in 2005, the Bachelor of Applied Science in System Design Engineering in University of Waterloo. Then she moved to University of California, Berkeley, and she got her master and PhD both in control systems in Berkeley. And then she moved to Europe to ETH Zurich in Switzerland. So now she's professor in automatic control laboratory of ETH. Maryam's research field is about decision-making, optimization, and control of large-scale uncertain systems, like power systems, like robotics systems, and air traffic systems. And I would like to mention that Maryam recently in the past year, she got very prestigious awards, for example, ERC, EU's ERC grant, and also a couple of grants from NASA. So Maryam, thanks for coming, and the stage is yours.
Thank you very much, Java.
And you know how to use this, right?
Yes, that's very cool. We need one for you. ETH. Yep. Okay, so good morning, everyone. It's my pleasure to be here with you in this last lecture. As Jalal mentioned, my background is mainly automatic control, and over the past few years, I started working with some colleagues in power system, and they sort of approached me about a control problem in demand response, and I found it so fascinating that I've been a little bit dragged into this area. And the kind of research in this area that I do is mainly game-theoretic. So yesterday you had very nice introduction to markets and also this idea of like assumption that the participants were price takers, okay? And so today basically we're gonna look at what if participants are not price takers but price makers. So in reality a lot of times generators or any market participants, they want to strategize to maximize their own benefit. And so what kind of tools we can use to analyze their decision making and the resulting market. So I hope to give you a little bit of introduction into this topic. And I prepared some notes which you find online, and I'm also projecting them. I hope that it's easy to read, but everything I say is also in the notes. It's an extended set of notes based on some of the lectures I had done before in ETH, but I sort of prepared them in some topics that I thought could be relevant for you, and there are more discussions and also exercises for you to try. And so let's just kind of go over like what we're gonna hopefully try to cover in this almost 3 hours. So I'll start with what's the introduction, motivation for looking at strategic decision making, and then I hope to cover 3 main topics briefly. One is games with continuous action domains. Okay, so this is when you're choosing your decisions from a continuous, from RRN, okay? And we're gonna look at how do we characterize Nash equilibria, in which cases they exist, and in which cases they're unique, and briefly we'll talk about how do we compute them. And then I wanna talk a little bit about auctions, and we're gonna look at just a standard first price, second price auction, and try to analyze them from a game-theoretic point of view, and characterize their Nash equilibria, and then we're going to briefly go into games with incomplete information, okay? So if you don't know, so a lot of these games, when you analyze them, you assume you know the rules of the game or the strategies of the other players. But in power markets, a lot of times you don't know who else is in the auction, and you don't know what is their strategy set and their true cost. So are there any questions? Are there any wish lists that you hope to learn from this lecture or cover? Good. So okay. So this is a little, so basically my lecture notes, it's sort of like the lecture notes I prepare for my teaching, so there's more discussion. I'll try to give you a summary, but let's think about motivation of why we think about the strategic decision making. So the first example, let me just show you this with a slide, is just a simple LMP market, and you're so there are just three generators and one demand, and there are some line limits, and you have the constraints arising from nodal balance. And then you see, for example, these are the curves that the generator 1, 2, and 3 may offer. Okay, and the system operator then needs to figure out an efficient dispatch. I think you saw these problems in the first couple of days. And then, so if you look at, so these are constraints. And then if you look at the LMP outcomes in this case, so P is the payment, and U is the utility, so how much profit you're making, okay? And so you see that generator 3 is the winner and is making $40 profit. And then by slight deviation, if generator 3 increases their cost curve, is going to basically make more profit. Okay, so these examples are not very hard to come up. Okay, so basically, it's in this case it's a price maker because it can slightly deviate. If the original one was true cost, by slight deviation, it has sufficient market power that it can sort of affect the outcome. Okay, so we're going to try to look at these. How can we analyze this strategic decision making, and how can we design markets that avoid these potential overbidding? Okay, so another example that I have in the notes for you is just a sort of a real-time pricing idea. So suppose that you have, maybe I just write here. So the first example was a strategic bidding in LMP market, and another very simple example is real-time pricing. So suppose that the price function is a function of the total consumption, and the motivation is that you want to make sure that the consumers, they switch their consumption to the times when there is high renewable penetration. So you can just think of a very simple price model where the price is, this is just a simple model. At time t, it's the total consumption minus the renewable. So this is renewable. This is consumption of player or consumer J. Okay. And then suppose that we just have two periods where in the first one R1 is 0, in the second one so at time 2 R2 is some 4, and we have 10 consumers, and then some of their consumption over time 1 and 2 should be 1. And so basically the point here is that if the consumers don't think about, they don't assume that their price also makers, they affect the price, they will all shift their consumption to the time that when the price is low, when there is more renewable, and then that consequently will increase the price, and everybody will be worse off. Okay, it's not very hard to sort of evaluate what, so if they don't take into account that they're affecting the price, and they just take the price as given, so they're assuming they're price takers, the consumption will all go to period 2 when we have renewables. The price will, everybody will end up worse off. Okay, and this is sort of another example that you have to think about. Like, we can be price makers in the market, whether it's in the markets that Jalal talked about yesterday, or even in the more sort of consumer-centric markets. Okay, yeah.
I was just going to type, does it matter if you have nodal or sovereign pricing?
What? Sorry. Oh, this one. Wait. Let me try this. Okay.
Is it if you have nodal or zonal pricing, in which case, like, do you have the biggest problem with this kind of strategic behavior and what?
So you will have, as long as the price is a function of what your your bid, then you can be a price maker. Yeah, so it will be the same. So this could also be nodal, but even in nodal pricing, those lambdas are a function of the bids in reality. So the price taking assumption may not be very good because some generators or consumers may have market power. Yeah, does it help? Okay, so let's do. So we'll learn the tools to discuss this, but before that, let's talk about, I'm going to give you an exercise, and just to, you can work on it. Actually, I shouldn't show this because I have the solution here. So when I give lectures, I don't look at, let me just, I make the blue invisible in my lectures, and then I post it 1 week later, but here, since we only have one time together, it's harder to do that. So I'm just gonna, okay, we'll go to the previous page, and I just put the problem here for you. So we're gonna think about a Corno electricity market and Corno competition, which you heard about. Just as a warm-up, also helps to kind of see your background in game theory and see how we can proceed. So we have, let's say, 2 generators. So generator 1 and 2. And the price, again, is sum A minus B, x1 plus x2. And then, so the marginal cost, let's say, of each generator, let's say, is C. Okay? So then the question is, so this is the production of generator 1 and also production of generator 2. Okay. So the question is, how would each player minimize her loss or maximize profit? So what's the xi star for I1, 2? Okay, so let's just take 3 minutes to come up with an answer. So I want you to solve for xi star as a function of these parameters. Is the problem statement clear? Okay, just as a warm-up, let's say you have 2-3 minutes to answer this question, and then we'll sort of start with this and build more complexity. Let's see if I can display the problem without. Okay, good. So time is up. All right, let's just hear what you came up with. So, does anyone want to share the answer?
Do you want the actual formula, or?
Yeah, just how you approach the problem?
So, yeah.
Okay. Oh, Mike.
Basically, just put the profit function down. That's going to be the price minus the cost times production. For one of the two generators, it's the same. It doesn't really matter. So x1, for example.
Good.
Yeah,
Actually,
and then of course you can.
Loss. Let me just put. Yeah, that's fine. Good.
Yeah, of course you can substitute the price expression in. Then you basically just take the derivative, set it equal to 0, and you have it.
Any other ideas? Yeah.
Oh, sorry. Yeah, what we can see here is that both generators share the same marginal cost. Then in the problem setup as we have it, they should have the same bidding decisions.
Yeah.
And then now if we take this marginal derivative with respect to x1, for example, we can then say that, yeah, well, x2 will have the same condition, and then we can set them equal.
Exactly. Good. So there's symmetry in the problem. So in this case, it's easy. Good. Any other comments? Yeah?
It will basically depend on whether each of the generators assumes the other's production is constant, or they try to predict the other's decisions, and there will be different solutions.
Okay. Good. Yeah, I see.
Yeah, but like if you even try to take derivatives in this formula, the answer would depend on another variable, because we have a product of x1 and x2.
Very good. So yeah, this is sort of, that's why exactly we need, it's not just a single optimization, but it's a game. So let's just, actually, if you don't mind, I'm going to put C minus P because I'm talking about losses and minimization in most of the report. So if you just put this, you get A minus B x1 plus x2 times x1, for example, for generator 1. And generator 1 needs to optimize her cost function. So it's going to, and this function, this loss is strongly convex in x1 decision, right? Because it has a positive coefficient in front of its x1 squared, right? So you can, to find the optimal solution, you can take the derivative and set it equal to 0. I think I'm missing a brackets here. Good. And if you take the derivative with respect to x1, what you should get is C minus A minus B x1 plus x2 minus B plus B, right? Do you all get C minus B times x1. So derivative of, like you use chain rule, so that's the first part. And then that's the derivative with respect to x1, and then derivative of the inner function plus b times x1. Okay. And as you mentioned, now the decision x1 is coupled with x2, right? But the x2 generator 2 will do the exact same thing. And I won't continue writing, but the equation that we'd get is, so this is the j1 die x1, and then the j2 die x2. Once you do the computation, you get C minus A minus B. As you mentioned, it's symmetric. Plus B x2 equals 0. Okay? And then we have to simultaneously solve these equations. We have two equations, two unknowns. It's pretty straightforward. So we get, and because it's symmetric, you get x1 equals x2 equals, let me see, what's the A minus C divided by 3B. Okay. So which makes sense in terms of if the marginal cost is more, this will decrease, and so on. You can make sure that it makes sense. But okay, so the point is that it's not a single optimization. Both both players are trying to optimize their decision, and so they both, if we get a system of two equations in two unknowns, and we can solve this. And that's exactly the idea of Nash equilibrium in general. Okay. Now, how would your answer change if, what if x1 and x2 had to belong to some, there was some capacity constraint? Okay. How would you answer this question? You can, let's ask from somebody I haven't heard before. Or you're also welcome to just briefly discuss with neighbor and then share your answer. All right. Someone has something to share that I haven't heard before. How about you guys? Do you have some thoughts? Let me give some hints. So we still need to find a minimum, like each player still tries to minimize her cost, but now subject to a constraint. So what tools did you learn already about constraint optimization? Something I haven't heard before. Yes?
So can we just do it in much the same way with the Lagrangian? With the Lagrangian?
Yeah, you can read with the Lagrangian. Yes, good. And what would it look like?
So then we've got the same thing, but plus the Lagrange
multiplier.
Plus the Lagrange multiplier multiplied by the constraint.
Yes, good. And then you try to solve the using KKT condition, for example. Yeah, good. So that's one way to do it. Any other ideas? Did you? Yeah, you can. Okay, you can go.
Yeah, so this is one way of doing it. The other way would be that first we see if our solution still works.
Yeah.
And if it does, it's fine. If not, then we know that the solution is on the boundary. So then instead of using the two equations that we got there, we use only maybe one equation and then say that the other one lays on the boundary of the feasible region.
And you would try all the boundary points, basically.
Yeah, it takes a while, yeah.
Yeah, it's so good. So these are all reasonable ideas. So we're going to look at basically also one more approach which would generalize even if your decision space could be Rn or a larger dimension where it may be hard to check all the boundary points. And basically the idea again is using first order optimality condition, because here we have convexity. And if you have a convex function that you're trying to minimize, then the first order optimality condition, so for each player, says that, now I'm writing general, in this case it's just a scalar, you don't need a vector, but for all feasible choices, okay? And you can try to find an x that satisfies, this is exactly, if you have a convex optimization, this is exactly a first order optimality condition. And you basically can write for both of the players and try to solve this system of equation. And we're going to look at what this means and how we can solve this, okay? But before that, let's just sort of do a brief recap of, so exactly in this example, what you computed is a Nash equilibrium. So what's a Nash equilibrium? If you have n players, and each of them has a cost function. And it's not a single optimization because each have a cost function, but there's coupling. So the cost can depend on everybody else's strategies, as exactly as you saw. So a Nash equilibrium, so I use NE. It's a point, and I will use X as a stacked version of the decision variables in K1 times Kn, such that, can you all read? Okay. J of xj, x negative j, less than or equal to, I'll explain this in a second, x tilde j, x negative j. I hope you can still read for all x tilde j in kj. Okay. So let's just talk about it. So it's just saying that so if you fix x negative j is everybody else's actions, okay? Recall that each player's cost depends not just on her action, but everybody else's action. And this is saying that the cost of the player is, at this xj, considering action of others fixed at x minus j, is the smallest that it can be. Okay, so this is also called best response. Everybody is choosing the best response to everyone else's strategy. Okay, so why is it an equilibrium? Because if everybody is choosing the best response, no one has incentive to unilaterally deviate, because this is the best I can do given what others are doing. So it's an equilibrium. I don't have incentive to deviate. Okay. Good. So that's exactly what you already did. This is just putting it in a more general setting. And you can also consider action spaces that are coupled, but we start with decoupled action spaces because it's a bit easier. But you can say the same thing for coupled action spaces. Good. So then let's look at another example. So we want to see, okay, do Nash equilibria always exist? We can define something, but like what if it doesn't exist in a game? Now the players we have to find an action that simultaneously satisfies these best responses. So do they always exist? So for that, let's look at one more example, and this is a Bertrand model of competition. Okay. So you already saw the Corno. It's quite simple. You can extend it to multiple players. You can do many things. You can have different marginal costs. It's the exact same idea. And you can analyze it. What if n goes to infinity and so on? Same approach. But let's look at another model of competition. So we have, again, two generators. But this time, instead of deciding how much they produce, they will decide how much they will charge the consumer. So they're deciding the price. So decision becomes, the x becomes the price function. So xj, price, generator j charges consumers for, let's say there are two, as before. And production marginal cost, again, is C. And we assume that total demand is 1 unit. And all the demand will choose the firm that has the lowest cost. So simplified assumption. There may be other reasons consumers choose a firm. But let's say total demand is 1 unit, and all demand chooses fair generator with lower xj. And then you can think of two questions. Actually, good. 3, 4. So we can derive the Nash equilibrium, or try to think of what is the Nash equilibrium in this case, and then answer the question, what if each producer, each gen, has capacity to serve maximum 2/3 of demand. Okay, and so you can think about Nash equilibrium in the original case where they don't have capacity limit. Each one can serve the whole demand. Try to think of, based on this expression, what should it be? And then what if they have a capacity limit? Okay, and then meanwhile I'll erase the board, and then we can collect your answers and discuss. Oh. Okay. Okay, well that's okay, fine. Oh wow, this is very nice. Cool. I don't know what happened here. Okay, yeah, you can think about this again for 2 minutes. Then I prepare the board. Maybe I erase this one as we don't need this. Very cool. Oh, maybe I have to give one more piece of information. If x1 equals x2, let's say half of the demand chooses firm 1. Okay. Okay, let's just briefly go through this answer as well. So what is the loss? What is the loss of its generator in this Bertrand model? Let's see. There's a microphone is there. Maybe you can pass it to your neighbor. We do this game that we just go through. Yeah.
Well, again, it will be, I guess, the earnings minus the cost, or actually cost minus the production cost. Yeah. Okay. So the loss is marginal cost minus so because this is the price I'm charging, there is 1 unit demand, so this is times 1, that's why I don't have it there. And this is if, in the case if
x1 is less than x2 because everybody will come to this pair. Good. And then what about, let's just fill in, what if x1 equals x2? I just said that, let's say half of the demand chooses G1 and the other half chooses G2.
Then that would be like equal to, the marginal cost would be the same for the two. So yeah, exactly the same thing, and just now multiplied by 1/2.
Yeah. And then what if x1 is greater than x2?
Then it would be c minus x.
Actually, if x1 is greater than x2, then nobody will come to this generator.
Yeah.
So they will make 0 basically. They don't sell anything, and they will make 0 loss. Yeah. Good. Thank you. Okay. So this is a little bit different. It's sort of a discontinuous function, but we can still work out what's the loss in each case. And then, do you have any answer for the Nash equilibrium? Okay, you can choose somebody and maybe throw it to that. Yeah. Okay.
I don't even know what the question is.
I'm sorry.
I'm sorry.
Okay,
Yeah.
maybe. What's the Nash equilibrium price that the firms would choose if they want to each optimize their own profit or minimize their loss?
No, I don't know.
So J2 has exact same structure. Okay.
Well, I think that in this case, in the Nash equilibrium, each producer fixes a price is equal to its marginal cost.
Yeah. And why?
Because in any other case, the other producer has an incentive to deviate in order to catch all the demand.
Yeah, perfect, exactly. So you can sort of, yeah?
Is this one period or multi-period?
Let's say it's one period, okay? Let's say one period, simple. And then you can see that, okay, so Nash equilibrium, each player should choose marginal cost, because as soon as, suppose just take player 1, and as soon as it goes above its marginal cost, it will lose all the basically consumers, because they will choose the producer with the smallest marginal cost, okay? And being below marginal cost, it means you will make losses rather than profits, so you have no incentive, okay? And you can verify that this is the only Nash equilibrium. If you pick any other x1 and x2, basically you have incentive to decrease the cost so that you can attract all the consumers, okay? So there is the Nash equilibrium exactly equals marginal cost in this Bertrand, in this simplified model, okay? Now, if there is capacity limit, though, the problem becomes a little more complicated, because I can charge slightly above my marginal cost, and because I have a limit and I can't serve all the capacity, then I will have some consumers and I will make profit, okay? And so basically you can show if there is capacity limit, there exists no Nash equilibrium, okay? So the way to show no Nash equilibrium exists, and the way, one way to show that is you can basically, you can think first starting with something that's not marginal cost, and obviously you have incentive to decrease it so you get more of the consumers. But as soon as you're equal to your marginal cost, you still have, you actually have incentive to be a little bit above it, because only 2/3 of the consumers will go to the one firm who's at marginal cost can only take 2/3 of the consumers. So the 1/3 will still come to you, okay? So basically you do not find, because this Nash equilibrium, you have to find the strategy sets needs to be best response simultaneously, and it may be that there's no Nash equilibrium. You cannot find a point that satisfies both conditions at the same time. Okay, so you can, I wrote more detailed description in the notes if you want, but the point of this was that just trying to find, first you need to think, okay, does this game has a Nash equilibrium, okay? And by the way, so here there is no, what you can show is that there is mixed strategy Nash equilibrium, which we won't have time to go in detail, but it means that rather than choosing one single number, x1, they can choose a probability distribution, and then you can show that that probability distribution satisfies the Nash equilibrium property. So that's called a mixed strategy. So no pure strategy Nash equilibrium exists, but mixed strategy Nash equilibria can exist in this case. Other questions? Yeah?
All this maths that we're doing is assuming that everyone is perfectly rational. So
yeah,
every
that's right.
player is doing the same kind of reasoning.
Exactly.
Correct?
Yes, that's a good point. So
as soon as you take away that assumption, basically you have no Nash equilibrium, right?
Well, we have to figure out a different way to analyze, I guess. But we are assuming they're rational. They want to minimize their loss or maximize their profit. Yeah. Yeah.
Are there methods how to analyze these things without considering complete rationality?
I know there are methods, but I haven't worked on them personally. So. Yeah, there are for sure methods. Economists sort of look at these problems. What if there's a notion of prospect theory, like if you don't have perfect rationality, but I don't know enough to, yeah, for sure there are methods. But I think it's interesting to actually bring those methods to energy systems. I don't think they've been as explored. Yeah. Other questions? Okay, so now we're going to look at, okay, can we know a priori for which games Nash equilibria exist? And I just give you sort of the result that's the theorem, sort of the sufficient conditions for existence of Nash equilibrium, okay? So if the decision spaces, so decision space K subset of, let's say we had, each player had this Ki, which was, or Kj, subset of some, let's say Rn, little n. I just try to make it as general as possible, but, and then Kj subset of Rn, compact and convex. And Jj is continuous, so it's a map. It's going to be a map from all the strategy spaces to R, continuous, and convex in Xj. Then a Nash equilibrium exists. Okay. And the proof is in your notes, but just to note that this is just a sufficient condition. So there may be cases where you have Nash equilibrium even if these sufficient conditions are not met. But these are sort of, it's harder to come up with necessary conditions, so you have to analyze game by game. So for example, in this case, the j's were not continuous as a function of x1 and x2, and we couldn't conclude using this result that the Nash equilibrium exists. Okay. In the corner model that you looked at with bounded action spaces, you had compact and convex decision space, and j's were continuous, and also they were convex in each player's decision space. So there was a unique Nash equilibrium. But with unbounded action, we actually found the Nash equilibrium, even though it didn't satisfy this condition, the compactness condition, and that's another reason that you can see this is just a sufficient condition. But it's a good sufficient condition. You can kind of, it makes usually sense to have some compact action space, some bound on what you can, for example, produce. Okay, and now we briefly also want to talk about how to characterize and compute them. And we already looked at this. So suppose they exist. We're just going to look at what we did already for the corner model and a little bit generalize it. And so basically the idea is you will learn one more tool in addition to KKT conditions that you've already seen to be able to analyze this. Any questions? Okay. So how to compute Nash equilibria, assuming they exist, and we're going to assume that these conditions are satisfied. And basically, we're going to use the fact that each player is minimizing their decision, considering other players' action fixed. Okay, so let's further assume J is continuously differentiable in xj. So we have the derivative in my I can take the derivative with respect to my action. Continuously differentiable in xj. Then we know that first order optimality condition, okay, and convex in xj, sorry. That was already part of the assumption of existence. Gradient xj, jj. So game theory, there's a lot of bookkeeping with the indices. So player j's cost function, you take the gradient with respect to her actions. We did that for kernel model, fixing other players' decisions. And this, you get a vector, because this is a gradient vector, times x tilde j minus xj greater than or equal to 0 for all x tilde j in kj. Okay, it's first order optimality condition. And then using this, because this holds for every also j, we can stack them together and get what's called a variational inequality that we need to satisfy. Okay, so let's do it like this. I'll just stack each player's gradient, j1 with respect to x1, x1, x negative 1, xn, jn. X tilde 1 minus x1, x tilde n minus xn for all x tilde n k1, k. Okay. This was first order optimality condition. And you can show that this holds if and only if this holds. So now this is, each of them is a vector of gradients. We're stacking them together. And if we take the inner product with x tilde, which is, again, remember, this is putting all actions together. We should get, we should be positive for all x tilde feasible. Okay? So this is, again, first order optimality condition in convex optimization, but because we have these couplings and we have each player has their own cost, we need to simultaneously satisfy this. Okay. And so this problem is the problem of given some, let's call this is called a game map. Let's use F gamma. It's called game map. That's what I use in your notes. And the problem of, actually now, I'd like you to see that, and I will use, okay, this is very cool. Just finish this part. So a variational inequality problem. So this problem of finding the x that satisfies this is called a variational inequality problem. So let's just define that and briefly say in the next 5-10 minutes how one way to compute solution to that. Oh, that one I did. Okay. So let's call this VI. Okay. Given some F map and K, I just write the problem abstractly. find x such that, sorry, f of x transpose x tilde minus x greater than or equal to 0 for all x tilde in K. This is the variational inequality problem. And then you see that solving Nash equilibrium is exactly an instance of a variational inequality problem where, well, let's try, x tilde is the stacked actions, and f is the gradient of the cost of each player with respect to her own action. Okay. Okay. Why? Then you may ask, why is this useful? We just formulated a problem to another problem. Any ideas? Has anyone seen VI before? Yeah? Maybe.
Not all.
What?
Should I say something? I don't know.
Why do you think it's useful? Why is it useful?
Not all variational inequality problems are Nash equilibrium problems.
Yeah, sure. Not all of them.
So some of the problems we have to see bigger picture in some of the problems.
So we already assumed that J was convex. So J has to be convex in the this J cost of each player needs to be convex in her decision space, so that we can write the first order optimality condition like this. And if this holds for every player, then it's exactly a variational inequality problem. Yeah. But in games, I think maybe where you're going at, if we had coupling constraints between the actions, then there may be not all variational inequality solutions. They don't capture all the Nash equilibria. They only capture a subset. But when we have decoupled actions, as we started here, every solution to this is also a Nash equilibrium. Okay. Yeah.
Thank you. Could we formulate this as a convex feasibility problem?
Yeah. Yes, there are different ways. Yeah, exactly. There's different ways to solve it. It looks like a feasibility problem. It's a convex feasibility problem. So what's a convex feasibility problem?
We try to find a feasible solution for a convex optimization problem.
Okay, and what's the objective here? How would you choose the objective?
Yeah, you don't have an objective. There's no objective. Yeah.
Yeah, just any feasible. Yeah. Okay, and what's the constraint? I guess this is exactly the constraint. So this, you need to find an x tilde that's an x that satisfies this for all x tilde.
Yeah.
Yeah. So you can formulate it like this. I wonder if there is a way to solve that efficiently. But yeah, exactly, it's a feasibility problem.
I think there should be a way to solve it.
Other questions, comments? Okay, I just want to, because it's sort of a brief lecture, I want to just give you one way to, and there are many ways to solve this, but the point is that these problems are very well studied, the variational inequality. And why? You may think, why are they very well studied? It's because it doesn't only capture Nash equilibrium. If you had a single optimization problem, this will be just a first order optimality condition. And so solving this means solving for the optimal solution. But there are more general problems that can be formulated. I think LCP problems also can be formulated as a VI. It's not my expertise, but I know that many class of problems can be formulated as VI. So they've been well studied, and we're going to look at one way to compute their solution. I'll just briefly comment about it. Good. So how to solve star? And the idea is to write the solution to this as a fixed point of an operator. Okay, so let's use this, that. Okay, maybe we use this word. So we looked at Korno and Bertrand model, and we looked at what's a Nash equilibrium, do they always exist, how do we characterize them, and now we're just briefly talking about once we have a characterization, how do we compute them. Okay. We're back to this question of how to solve a star, because if we solve a star, then we can find the Nash equilibrium. Yeah?
Maybe just before we do this, I'm not quite sure if I understand the dimensions of f correctly. Is it? I thought f was a vector.
Yeah. It's a map from Rm to Rm. So it can take an x in Rm, and it gives you a vector. Now, in case of the game, x is the stacked vector of decision. So if each player, for example, if there are n players and each of them, so this is the game case. If each of them is in Rn, then f will be a map from Rn little n times to Rn little n. Does that help? Okay. It's always good to write what's the domain and what's the range. It helps clarifying many things. Okay, thank you. Good, so x solves star if and only if for all lambda, let's call them a step size, x is the fixed point of this operator projection onto k of x minus lambda f of x. Okay? So this one is in Rm. This is just a constant. This is in Rm. So the intuitive idea is this is kind of like taking a step in the opposite to the gradient. If this was gradient of a single function, you project it on the constraint set, and any fixed point of this operator, so this operator, what it is, so it's, we can write it as x equals, we can start with some x0 and then sort of compute this operator, f of x0, and then we get x1, so xk plus t plus 1 is equal to f of xt, where f is exactly this projection onto k of x minus gamma f of x. Okay. Okay. So this is just saying that x solves the variational inequality problem if and only if for every lambda, x is fixed point of an operator that takes x itself and gives you a new vector that comes from projecting x minus lambda f of x to the set. Okay, so let's just look again what's happening and then why it's important. Actually, maybe no. I don't know. I think I am here. There are some sort of exercises in the notes, but basically we are here at the bottom. So x is solving this variational inequality problem, which is characterized by k and f, if and only if x is a fixed point of this projection operator composed with x minus lambda f of x. Okay, so that's where we are. So it's taking basically if this is k and this is x minus lambda f of x, and then we project it onto this set. So this is the point that we find the point that minimizes the distance to x minus gamma f of x, and it's in the set. And this fixed point is the solution of variational inequality problem. And you can show that. I mean, in the text you can follow. It's written there. Okay. And so then the idea, how do we how do we find this fixed point? We're still kind of massaging problem, and we're going from one problem to another problem, right? But it's not quite clear if it's still useful, because we went from a Nash equilibrium problem to a variational inequality formulation of the Nash equilibrium, and now we are saying that the solution to VI is a fixed point of the operator. Okay, we're just sort of reformulating our original problem, but the point is that finally this is something we can compute. The idea is that, so how do we compute X? If we can design this F to be a contraction, so this gamma is our design variable, it's a step size, and if we can design F to be a contraction operator, then you can make sure that then you, from the contraction mapping theorem, you know that if you keep applying this, you will converge to the fixed point, okay? So how do we compute X? Choose gamma step size so that the map X taken to projection onto K of X minus gamma F of X is a contraction. If this is a contraction, then from contraction mapping theorem, and this is in your notes in the appendix, just as a reminder, we know that starting from any initial condition, the iteration project K x t minus gamma f of xt will converge to the fixed point, converge to the unique fixed point. Okay, good. So I think this is sort of the main, and then in the notes you see the proof of, I included the proof of why is this how we can make this a contraction by choosing gamma, and then the proof that there is the convergence. Okay, but what I want to highlight about this is that this is it's another powerful way of solving optimization also problems. It's the projected gradient descent, if you think of the optimization, right? Why does it work? Basically, you make sure that this function becomes a contraction, so if you're iterating, you will converge to the solution. It's the same idea. By formulating the game as a variational inequality problem, we made a connection between Nash equilibria and optimization problems, and that means that we can use some of the tools such as projected gradient descent to find the Nash equilibrium, okay? And so you can go back to the Cornell example and try to address the constraint case with this method. You can also compare it with other methods such as Lagrange, as you suggested, or different ways of trying the boundary points. This is one way to find Nash equilibrium. It's quite general. It also applies if your decision spaces are in larger space. For example, if you have to choose the vector of consumptions or production over a time period, and if you have some coupling constraints between the decision variables, and there's some exercises in the note that you can also try to solve them for those cases. Other questions? Let's just pause now. Yeah.
Curious if we can use this VI concept to give some characteristic to the game without actually solving it.
Okay.
Can we predict the outcome of the game having this VI formulation?
Okay, interesting idea. What would you want to predict, for example?
Since it has gradient function, I would love to see whether player approaches Nash equilibrium in reducing action X or increasing it, at least. Like, can we predict this direction of Nash equilibrium?
Okay, yeah, very good question. So there are two things I can think of. One is you can think of, okay, could these players converge to Nash without, because at the moment it looks like it's a centralized operation, but if they have decoupled actions. Actually, you can do this projection in different coordinates for each player, and it will be sort of each player will then needs to have very minimum coordination with other players, just needs to run a projected gradient descent on her own decision variable, and then you get to convergence as long as the gamma that each player is choosing satisfies conditions for contraction. So that's one way. For example, if players don't want to coordinate together, of course, the function f in the game, to know each player to know her gradient, because it's a game, it depends on others' actions. But in several games in electricity markets, they have this property of being aggregative games, meaning that as long as you know some aggregate behavior of others' actions, you can still compute this gradient. So it's minimum coordination. The other way you can use this to get insight is that it turns out that if this gradient function is symmetric, then there is a so-called potential function for the game, which means that there is one single function that all players are trying to optimize, okay? But that's not always the case, only if this gradient function is symmetric. Yeah. There was another question? Yeah, you can throw it. Oh, yeah, there.
One, it's about these aggregative games,
yeah,
right? So to some extent, an aggregative game, at least in an optimization framework, an aggregative problem is an exchange problem, can be also seen as a consensus problem. Is that the same on this case? And second question, you said that you can use different gammas for different players in case of decentralized, like distributed game solution, right? As long as you satisfy the contraction, that the map is a contraction. Can you change the gamma along the iteration as long as it keeps a contraction? So there's no hypothesis on keeping the gamma fixed per agent.
Yeah, you can also change gamma over time.
So you can do like first step big and then going smaller beginning.
Yeah, exactly. Yeah. You can choose a time varying gamma. It may have better convergence properties. I don't remember off the top of my head because the convergence rate depends on sort of the minimum eigenvalues of these maps. So you may be able to choose time varying gamma to have faster convergence. And about aggregative games and consensus. So if maybe think of, and the examples, the exercises at the end of the notes, the problem sets, they're examples of aggregative games. So you can try to compute these gradients, and you will see that each player's gradient just depends on some of other players' actions, for example. But there still needs to be some central coordinate that gives them that sum, okay? Or if they have coupled actions, then there needs to be a central coordinate that gives some multiplier about the coupled actions. So there is, it's decentralized, but there is minimum coordination needed because after all, it's a game that decisions are coupled. So the players don't need to pass individual strategy sets or preferences, but they need to know some aggregate notion of the decision of other players. For example, in the aggregative games in real-time pricing, if they know just the price, which is a function of total demand, then that's sufficient. Then about consensus, so there are some works that try to solve this using consensus. I have a bit of philosophical thing against it because it's a Nash equilibrium problem, and the principal idea is the agents are non-cooperative. And if you're doing consensus, you have to share information. Of course, you can do that. You can see it as a sort of distributed and do consensus, but then it seems to me it's sort of against the assumption that we are non-cooperative because the decision, the solution concept of being in Nash equilibrium means that everybody selfishly optimizes her own cost function. If you were actually allowed to cooperate, maybe you just want to go to the central solution, which might be better for everybody. And that's also brings us to another notion that Nash equilibria may not be efficient in the sense that there may be, if a central planner is optimizing some of all cost functions or some other single function, we may get more efficient solutions. Yeah. Other questions? Yeah.
Now, the way we have written it down, it seems like every market player will solve this, will compute the Nash equilibrium, so they will all solve more or less the same problem. And wouldn't it be much more efficient if there could be one person in the middle that they all trust, who solves this problem for them only once and then tells them what to do?
Yeah, that's a good question. So I guess it brings two issues. One is if they would trust sending all their sort of marginal costs and their sort of maximum minimum demand to one central operator, and the other one issue is a scalability. So if one player wants to solve this and you have maybe 1,000, 10,000 players, it becomes, anyways, you will do it probably in a distributed way because it will be more efficient. Yeah, but yeah, so basically in terms of efficiency and privacy, it might be still better if you try to do it locally. Does that help? Yeah.
I'm not sure. I think it, yeah.
Or maybe you can try it in the problem sets. You can try for large n and try to solve in a central way and then try to solve in it.
Yeah, because it seems like you need to find a fixed point to this contraction mapping.
Yeah.
So if and you need to do this only once, it seems, no? And then you have the Nash equilibrium, so you know what everyone else is going to.
Well, finding the fixed point to a map is non-trivial. So the whole point of the iterative approach is to, because it's kind of like solving a nonlinear equation, right? You're solving, you're finding x minus f of x equals to 0. So some g of x where g is some nonlinear function. You're trying to find this x. So it's a non-trivial computation. So the iterative way is one way to do it. It's just make sure that you will converge to it.
Exactly. It's a hard problem.
Yeah.
But once you found the solution, you have solved the problem for everyone. No? Once you found the Nash equilibrium, you know what everyone else is going to do as well.
Yeah, but in the decentralized way, everybody is not repeating that. Everybody is just doing, okay, maybe it wasn't clear. So everybody will just do their own coordinate of this. So I will just put an x, let me use a different color. They will not all try to solve this equation. Rather than they will all do xj k plus t plus 1 is equal to, this is kj, xj, and gamma j, and fj. So they are solving a smaller iteration. Yeah, does that help? Okay, great. Thanks for the question. Yes, so now we take a break, perfect timing, and then after 15 minutes? 10, 15. After the break, we're going to switch topic and we're going to look at auctions. So this is what I want to say about continuous action games. Usually, if you have some convexity assumption, then maybe there are some ways you can solve them. Then we're going to look at auctions, and basically we'll briefly discuss auctions and then and games with incomplete information.